In the beginning, we look up at the night sky and see only points of light, stars scattered like diamonds across a black ocean. But what do those lights really represent? Each one is a sun, often far larger and brighter than our own, and each may host its own worlds, its own mysteries, and possibilities for life. To grasp the universe, we must first confront its scale. Let's start with something familiar: Earth. Our planet, just over 12,000 kilometers in diameter, feels immense. It's home to towering mountains, vast oceans, sprawling deserts, and lush forests. Walking across it would take a lifetime. Yet, in cosmic terms, Earth is barely a grain of sand. Now consider the Moon, our closest neighbor in space. At nearly 400,000 kilometers away, it's so distant that light takes more than a second to reach us. When the first humans traveled there in 1969, they crossed a gulf so vast that Earth appeared as a fragile blue marble suspended in the void. Next, we have Mars, Jupiter, and Saturn with its spectacular rings. Even at the speed of light, messages between Earth and these worlds take minutes to arrive. The farther we venture, the more time stretches, and communication becomes delayed. Space begins to feel immense, and yet we have only just begun. Our solar system spans about 150 astronomical units across. That's 150 times the distance between Earth and the Sun. For a spacecraft like Voyager 1, traveling at over 60,000 kilometers per hour, it has taken more than 40 years just to reach the edge of our cosmic neighborhood. But the solar system is tiny compared to the Milky Way galaxy. The Milky Way stretches across 100,000 light years. That means light, the fastest thing in existence, takes 100,000 years to cross it. Our Sun is just one of 200 billion stars, orbiting quietly around the galactic center once every 230 million years. Even the Milky Way is small when compared to what lies beyond. Our galaxy is part of a cluster called the Local Group, which belongs to the massive Laniakea supercluster, a web of galaxies stretching hundreds of millions of light-years across. At the largest scales, the universe resembles a vast cosmic web. Galaxies and clusters form filaments, stretched like strings across space, with enormous voids in between. These filaments extend for billions of light-years, connecting the universe into a structure too vast for human imagination. The numbers become overwhelming. Billions of stars, billions of galaxies, billions of light-years. But perhaps the most humbling fact of all is this: the observable universe is not infinite. It has an edge, a horizon. Beyond that horizon, light has not yet had time to reach us. There may be more galaxies, more stars, more mysteries, but they remain hidden, waiting. As we zoom outward from our planet, past the solar system, past the Milky Way, and into the vast cosmic web, we come to realize that scale itself is a kind of mystery. It's not just about size, it's about perspective. We are small, yes, but in our smallness lies the ability to wonder, to measure, to imagine, and that, in itself, is extraordinary.
In the vastness of the cosmos, the story of stars begins in regions known as nebulae. These are not just faint smears of light, they are colossal clouds of gas and dust, often stretching for dozens or even hundreds of light years. Within these stellar nurseries, tiny fluctuations in gravity start to gather matter together. It begins subtly, a ripple here, a cluster there. Over time, these ripples grow stronger. Gas attracts more gas, dust collects more dust, and slowly, the nebula begins to collapse under its own weight. As this material falls inward, the core of the forming star heats up dramatically. Temperatures soar from a few hundred degrees to millions of degrees Kelvin. At this stage, we have a protostar, a glowing, swirling ball of gas wrapped in the remnants of the collapsing cloud. Magnetic fields twist and shape the surrounding matter, while powerful jets of energy shoot outward along the star's poles. This chaotic dance marks the birth cry of a new sun. The true transformation occurs when ignition happens. At around 10 million degrees, nuclear fusion begins. Deep in the core, hydrogen atoms collide with such force that they fuse into helium, releasing enormous amounts of energy. In that instant, a star is born. It starts to shine, balancing the inward pull of gravity with the outward push of its own radiation. From this moment on, the star enters what astronomers call the main sequence, the longest and most stable phase of its life. For billions of years, it will continue fusing hydrogen into helium, radiating light and warmth across the cosmos. Every star we see in the night sky is in this stage of its journey, a steady beacon of energy against the darkness. But not all stars are created equal. The mass of the collapsing cloud determines the fate of the star. A small cloud may produce a red dwarf, dim, cool, and long-lived, burning slowly for trillions of years. In contrast, a massive cloud gives birth to a blue giant, hot, luminous, and short-lived, burning through its fuel in just a few million years. This diversity showcases the incredible range of stellar creation. We can even witness these processes from our own planet. The Orion Nebula, visible through small telescopes, is one of the nearest stellar nurseries. Inside it, hundreds of newborn stars illuminate the gas around them, sculpting pillars and shapes that stretch across light years. These regions appear almost like cosmic art, but behind that beauty lies the raw power of creation. Stars do not form in isolation. They are often born in clusters, with dozens or even hundreds igniting together within the same cloud. Over time, gravitational interactions fling them apart, scattering them across the galaxy. Yet for a while they remain siblings, shining side by side, linked by a common origin. The birth of stars is not just a spectacle, it is the beginning of everything else. Around these young stars, disks of leftover gas and dust swirl, gradually forming planets, moons, and asteroids. The story of solar systems, and even life itself, starts with the collapse of a nebula. Without star formation, there would be no worlds, no oceans, no living beings to ponder their existence. In a way, the birth of stars is the heartbeat of the universe. Even now, new stars are being born every second across the cosmos, as galaxies recycle their gas into fresh generations of suns. When we look up at the night sky, we are not merely seeing stars that were born billions of years ago. We are witnessing the universe constantly renewing itself, an endless cycle of light emerging from darkness. When I look up at the night sky, I see a scattering of stars. But through a telescope, I discover a much grander reality. Those stars are just a small part of a vast structure known as galaxies. Billions of stars bound together by gravity, each galaxy an island floating in the immense ocean of space. Our own Milky Way is just one of these cosmic islands, containing around 200 billion stars. Yet it's far from unique. In fact, the observable universe is home to an estimated 2 trillion galaxies, each with its own stars, planets, and mysteries waiting to be unraveled. Galaxies come in various shapes and sizes. Take spiral galaxies like the Milky Way and Andromeda. Their sweeping arms stretch out from a bright central bulge, filled with young, glowing stars and rich clouds of gas where new stars are born. Then there are elliptical galaxies, resembling glowing orbs or footballs, filled with older stars and minimal gas, often formed from galactic collisions. Irregular galaxies, on the other hand, appear chaotic, distorted by gravitational encounters. Together, these types create a diverse family of galaxies scattered throughout the universe. But galaxies are not static, they are dynamic ecosystems. Stars orbit their galactic centers, completing their journeys over hundreds of millions of years. Gas flows in vast streams, fueling star formation, while supermassive black holes at their hearts shape their evolution through powerful energy outbursts. A galaxy is not a frozen snapshot, it's a living entity, constantly changing and evolving. Galactic collisions are common, despite the vast emptiness of space. When galaxies meet, stars rarely collide directly due to their immense distances. Instead, gravity reshapes them, warping their forms and triggering intense star formation in a phenomenon known as starbursts. Over time, two galaxies may merge into a single, larger one. In fact, our Milky Way is on a slow-motion collision course with the Andromeda Galaxy, and in about 4 billion years, They will merge into a massive elliptical galaxy, forever altering our night sky. The beauty of galaxies is captured in stunning images from space telescopes. The Hubble Space Telescope has revealed spirals glittering like cosmic pinwheels and peculiar galaxies twisted into breathtaking shapes by gravity's dance. Each image is not just a portrait of a galaxy, it's a glimpse into the past. Because light takes time to travel, we see galaxies as they were millions or even billions of years ago. Observing the cosmos is like peering into a time machine. Some galaxies are astonishingly large, with giant ellipticals containing up to 100 trillion stars, while others are tiny dwarf galaxies, with only a few billion stars. Dwarf galaxies often swarm around larger ones, merging and feeding their growth. This constant cycle of formation, collision, and transformation drives the evolution of the universe on the grandest scales. Beyond individual galaxies, they rarely exist in isolation. They group together in clusters bound by gravity. The Virgo cluster, for instance, contains thousands of galaxies spread across millions of light years. These clusters link into even larger structures called superclusters, stretching for hundreds of millions of light years. At the largest scale, galaxies trace out a vast cosmic web, with filaments of matter connecting clusters and leaving enormous voids in between. The universe, at its grandest, is a tapestry of galaxies woven together by gravity. Galaxies are not just structures of stars and gas, they are archives of cosmic history. The stars within them record the chemical evolution of the universe, from the first hydrogen and helium created after the Big Bang to the heavier elements forged in supernovae. By studying galaxies, astronomers can read the story of how the cosmos grew from simplicity into complexity, from darkness into light. Yet, even with all we've learned, galaxies remain full of mysteries. Why do they rotate as they do? Observations show that visible matter, stars, gas, and dust cannot fully explain their motions. Something invisible, known as dark matter, seems to dominate their mass, holding them together. Without dark matter, galaxies as we know them wouldn't exist. This puzzle remains one of the great challenges of modern astronomy. In the end, galaxies are more than just islands in the void. They are cradles of stars, forges of elements, and potential homes for life. To study them is to explore the grand design of the universe itself. As I gaze at the countless galaxies scattered across the sky, I'm reminded that our Milky Way is just one small piece of a vast and beautiful whole. Every star that twinkles in the night sky has a story, a life cycle that mirrors our own. They are born, they live, and they eventually die. This journey unfolds over millions, even billions of years. Yet the stages of their existence are patterns we can trace and understand. It all begins in a nebula, a vast cloud of gas and dust. Gravity works its magic, pulling these materials together to form a protostar. When nuclear fusion ignites, the star enters the main sequence, the stable phase of its life. Our sun is currently in this stage, shining brightly for about 4.6 billion years, with another 5 billion years of stability ahead before change inevitably arrives. A star's destiny hinges on its mass. This single factor determines how long it will shine and how it will meet its end. Small stars, like red dwarfs, burn slowly and efficiently. They may be dim, but they can last for trillions of years, far longer than the universe itself. Remarkably, no red dwarf has ever died yet. The cosmos simply isn't old enough for them to reach that stage. When they finally fade, they cool into black dwarfs, dark remnants that no longer shine. Stars like our sun lead a more balanced life. For billions of years, they fuse hydrogen into helium. But eventually, the hydrogen in the core runs out. Gravity tightens its grip, squeezing the core while the outer layers expand, transforming the star into a red giant. This swelling can be dramatic, sometimes engulfing the orbits of inner planets. In about 5 billion years, Earth may be consumed by our sun as it grows. Inside the red giant, new layers of fusion ignite. Helium atoms fuse into carbon and oxygen, creating new elements with each burning stage. However, a sun-like star cannot fuse elements heavier than carbon. Eventually, its core becomes a dense ball of carbon and oxygen, while the outer layers drift away, forming a glowing shell called a planetary nebula. What remains is a white dwarf, the hot, compact core of the star, shining faintly for billions of years before it cools into darkness. Now let's talk about massive stars, those with more than 8 times the mass of our Sun. Their lives are short and violent, burning through their fuel at a furious rate, lasting only a few million years. When hydrogen is depleted, they fuse helium, then carbon, and continue fusing heavier elements, building layers like an onion. At the center, iron forms, but fusion of iron consumes energy instead of releasing it. This marks the beginning of the end. In less than a second, the core collapses under its own gravity, and the outer layers rebound in a catastrophic explosion, a supernova. The energy released is so immense that for a brief moment, the star outshines entire galaxies. These colossal events scatter heavy elements across space: gold, silver, uranium, and all the materials needed to build planets and life. Every atom of calcium in our bones and iron in our blood was forged in the heart of a massive star that exploded long ago. What remains after a supernova depends on the mass of the core. A core with less than about 3 solar masses becomes a neutron star, an incredibly dense object where a teaspoon of its matter would weigh billions of tons. Spinning rapidly, neutron stars emit powerful beams of radiation, appearing to us as pulsars, cosmic lighthouses flashing across the universe. But if the core is heavier, gravity wins completely. It shrinks into a singularity, creating a black hole where space and time are bent beyond recognition. Not even light can escape. The life cycle of stars is not just a tale of light and death, it's a story of creation. Stars forge the very elements that make up worlds, oceans, and living beings. Their lives and deaths are written into our bodies and our planet. As Carl Sagan said, we are made of star stuff. The calcium in our bones, the oxygen we breathe, the carbon that forms life, all of it was born in the hearts of stars, scattered across the galaxy to become part of us. In the end, the death of one generation of stars becomes the birth of another. Nebulae enriched with heavy elements collapse again, forming new suns, new planets, and perhaps new life. It's an eternal cycle, woven into the fabric of the cosmos. Stars are not just distant points of light, they are the engines of creation. Without them, the universe would be dark, empty, and lifeless. When I gaze up at the night sky, the Milky Way reveals itself as a soft band of light, a celestial river winding through the darkness. For centuries, people have spun tales about this mysterious glow, imagining it as a pathway for gods or the remnants of spilled milk from divine hands. But now, we understand that the Milky Way is our home galaxy, a magnificent spiral system filled with stars, planets, and cosmic wonders. Spanning about 100,000 light-years, the Milky Way is a vast expanse. If you could travel at the speed of light, it would take you 100,000 years to cross from one end to the other. Within this enormous disk, there are around 200 billion stars, along with nebulae, star clusters, and immense clouds of gas and dust. It's a bustling metropolis of the cosmos. The Milky Way's spiral shape is striking, with graceful arms that stretch outward from a central bulge. These arms aren't solid structures. They are waves of density where stars and gas are more concentrated. They are vibrant regions of active star formation, glowing with bright young stars and dotted with stellar nurseries like the famous Orion Nebula. Between these arms, dark lanes of dust absorb and scatter starlight, giving our galaxy its textured appearance. At the very heart of the Milky Way lies something extraordinary, a supermassive black hole known as Sagittarius A. This beast contains the mass of about 4 million suns, all crammed into a space smaller than our solar system. Stars orbit around it at incredible speeds, revealing its presence even though it remains invisible to our eyes. This central region is a chaotic, energetic place where gravity reigns supreme. Our sun is not located near the center or at the edge of the galaxy. Instead, it resides about 26,000 light-years from the galactic core, nestled in one of the quieter spiral arms known as the Orion Arm. Here, the density of stars is lower, providing a relatively calm environment for planetary systems like ours to form and thrive. It's in this cosmic suburb that Earth orbits, a tiny world among countless others. The Milky Way is alive with motion. Stars orbit the galactic center in paths that take hundreds of millions of years to complete, Gas flows through the spiral arms, igniting new generations of stars. Gravity binds the entire structure together, but it's not just the stars we see that hold it all in place. Dark matter, an invisible substance that constitutes most of the galaxy's mass, forms a vast halo around the Milky Way, shaping its rotation and stability. Without dark matter, our galaxy wouldn't be able to hold itself together. And the Milky Way isn't alone. It has dozens of smaller satellite galaxies orbiting it, like the Large and Small Magellanic Clouds, which are visible from the southern hemisphere. Over time, these dwarf galaxies are being torn apart and absorbed, their stars merging into our own. The Milky Way is part of the Local Group, a family that includes the Andromeda Galaxy and hundreds of smaller companions. In about 4 billion years, the Milky Way's fate will change dramatically. It will collide with Andromeda. While the vast distances between stars mean that direct collisions will be rare, gravity will reshape both galaxies, warping their structures and sparking bursts of new star formation. Eventually, they will merge into a massive elliptical galaxy, forever altering the view of our night sky. Despite its grandeur, we see only a fraction of the Milky Way from Earth. Our view is obscured by dust and gas, which hide much of the galaxy's structure. However, with radio telescopes, infrared observations, and space-based instruments, astronomers are gradually mapping its spiral arms, central bulge, and hidden regions. Each discovery brings us closer to understanding our galactic home. The Milky Way is more than just a collection of stars. It is the cradle of our sun, our planets, and our very existence. The heavy elements in our bodies, carbon, oxygen, iron, were forged in stars within this galaxy and scattered across space by supernovae, eventually finding their way to Earth. To say we are children of the Milky Way is not just poetic, it's a scientific fact. Yet, as familiar as it is to us, our galaxy is just one among trillions. From a cosmic perspective, it's ordinary, just another spiral in an endless sea. But to us, it is special, it is home. When we look up at the Milky Way's glowing band, we are not merely seeing distant stars, we are witnessing the history of our galaxy, the processes that gave us life, and the promise of a future among the stars. Chapter 6 dives into the fascinating world of exoplanets, those distant worlds orbiting stars beyond our solar system. The journey of discovering these planets has been nothing short of revolutionary, reshaping our understanding of the universe and our place within it. The first confirmed exoplanets were discovered in the 1990s, a breakthrough that opened the floodgates to a new era of astronomy. These discoveries were made possible by advancements in technology, particularly through telescopes like Kepler and TESS. Kepler, launched in 2009, was designed specifically to hunt for Earth-sized planets in the habitable zones of stars, those regions where conditions might be just right for life as we know it. TESS, or the Transiting Exoplanet Survey Satellite, followed suit, expanding our search to a wider swath of the sky and discovering thousands of new worlds. What's truly astonishing is the diversity of planets we've found. Some are gas giants like Jupiter, while others are rocky, similar to Earth. We've even identified super-Earths, which are larger than our planet but smaller than Neptune. The variety is mind-boggling, and many of these exoplanets reside in their star's habitable zone, where temperatures could allow for liquid water, an essential ingredient for life. However, studying these distant worlds comes with its own set of challenges. The vast distances involved mean that even the closest exoplanets are light years away. This makes direct observation incredibly difficult. We rely on indirect methods, like measuring the dimming of a star as a planet passes in front of it, to gather data. Each new discovery raises more questions than it answers, pushing the boundaries of what we know. The search for signs of life on these exoplanets is one of the most exciting aspects of this field. Scientists are developing new technologies and methods to analyze the atmospheres of these distant worlds for biosignatures, chemical indicators that life might exist. Imagine the implications if we found evidence of life elsewhere in the universe. It would fundamentally alter our understanding of biology and our place in the cosmos. The discovery of exoplanets has shifted our perspective dramatically. We once thought of our solar system as unique, but now we know that billions of potential Earth-like planets may exist across the Milky Way. This realization invites us to ponder profound questions about existence and the possibility of life beyond our planet. As we continue to explore and learn more about these distant worlds, we are reminded of the vastness of the universe and the potential for discovery that lies ahead. Each exoplanet we find is a new chapter in our understanding of the cosmos, and who knows what we might uncover next. The universe is full of mysteries, and we are just beginning to scratch the surface.
For as long as we've gazed at the night sky, the question has haunted us. Are we alone in this vast universe? The search for life beyond Earth is one of humanity's greatest scientific quests, intertwining astronomy, biology, chemistry, and our wildest imaginations. Each new discovery brings us a step closer to an answer. On our own planet, life emerged surprisingly quickly. Geological evidence shows that within a few 100 million years after Earth cooled, microorganisms had already made their appearance. This rapid onset suggests that, given the right conditions, life might not be as rare as we once thought. If life could thrive on a young Earth, could it also arise elsewhere in the cosmos? Scientists often start their search with water. Every known form of life depends on it, which is why the habitable zone around a star, where liquid water can exist, is so crucial. But water alone isn't enough. Life also requires essential chemical ingredients: carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. Fortunately, these elements are abundant throughout the universe, forged in the hearts of stars and scattered across galaxies. Here on Earth, we find life thriving in extreme environments once deemed inhospitable. From boiling hydrothermal vents at the ocean's depths to frozen glaciers and even acidic lakes. Organisms known as extremophiles demonstrate that life can adapt to conditions far harsher than what we experience on the surface. If life can endure here, why not on icy moons or beneath the atmospheres of distant planets? In our own solar system, several intriguing candidates beckon our curiosity. Mars, once warm and wet, may still harbor microbial life beneath its surface. Europa, a moon of Jupiter, conceals a vast subsurface ocean beneath its icy crust, while Saturn's moon Enceladus also holds a hidden ocean, with plumes of water vapor venting into space. These worlds may not resemble Earth on the surface, but beneath their frozen shells, they could host habitats suitable for life. Beyond our solar system, the discovery of exoplanets has revolutionized our search. Thousands of worlds orbit distant stars, many residing in their habitable zones. With advanced telescopes like the James Webb Space Telescope, astronomers are beginning to analyze the atmospheres of these planets. By studying starlight filtering through a planet's atmosphere, scientists can detect gases that might indicate biological activity. A mix of oxygen, methane, and water vapor could serve as a powerful biosignature, hinting at life. Imagine one day detecting a clear signal, oxygen levels that can't be explained by chemistry alone. While it wouldn't be definitive proof of extraterrestrial life, it would be a compelling clue. But our curiosity doesn't stop at microbial life. We also ponder the existence of intelligent civilizations. This is where SETI, the search for extraterrestrial intelligence, comes into play. Since the 90s, scientists have been listening for signals from other worlds using radio telescopes. So far, the universe has remained silent, but that silence doesn't necessarily mean we're alone. Civilizations might use technologies beyond our detection capabilities, or they could be too distant or too short-lived for us to find. The vastness of space complicates our search, akin to trying to hear a whisper across an ocean. Yet, even if intelligent life is rare, the sheer number of planets in our galaxy suggests there could still be many civilizations out there. With around 100 billion stars in the Milky Way, if even a fraction host habitable planets, the odds begin to favor the possibility of life. The famous Drake equation attempts to estimate the number of communicating civilizations, reminding us that our galaxy could be teeming with life, or we could be unique. This search for life is not just a scientific endeavor, it's a philosophical one. Discovering that we are not alone would profoundly alter humanity's self-perception, expanding our understanding of our place in the universe. Even if we find only microbial life, it would signify that life is not a miracle confined to Earth, but rather a natural outcome of the universe. In the coming decades, missions will explore the icy moons of our solar system, and new telescopes will scan distant planets for biosignatures. Perhaps one day, a signal will reach us from the stars. Until then, we continue our quest, driven by curiosity and hope, as the question lingers in the vast darkness of the cosmos. Is someone else out there, looking back at us?
Few objects in the universe inspire as much wonder and fear as black holes. They are the ultimate paradox, invisible yet immensely powerful. Imagine a force so strong that it bends the very fabric of space and time, trapping everything that comes too close, even light itself. A black hole begins its life with a massive star. When that star runs out of fuel, nuclear fusion can no longer hold back gravity. The core collapses under its own weight, and if the star is massive enough, nothing can stop the collapse. This leads to the creation of a singularity, a point of infinite density, surrounded by an event horizon. This boundary is not a physical surface, it's a one-way door. Cross it, and all paths lead inward. For an outside observer, an object falling into a black hole appears to slow down, time stretching longer and longer, never quite crossing the horizon. But for the falling object, the plunge happens in mere moments, leading to a place where our laws of physics break down. Black holes come in various sizes. Some are just a few times the mass of our sun, remnants of collapsed stars. Others are truly monstrous, with millions or even billions of solar masses lurking at the centers of galaxies. Our own Milky Way has a supermassive black hole named Sagittarius A, over 4 million times the mass of the Sun. We can't see it directly, but we can observe stars whipping around it at incredible speeds, pulled by its invisible grip. In 2019, humanity caught its first glimpse of a black hole. The Event Horizon Telescope, a network of radio telescopes around the globe, captured an image of the black hole in the galaxy M87. What we saw wasn't the hole itself, but the glowing ring of hot gas swirling at near-light speeds around the event horizon. For the first time, the shadow of a black hole was revealed, providing proof of Einstein's theory of general relativity on a grand scale. Yet, the mysteries remain. What happens inside a black hole? At the singularity, our equations fail. Space, time, and matter are crushed into something beyond comprehension. Some physicists believe we need new theories like quantum gravity to understand this hidden realm. Others speculate about wormholes or connections to other universes, though these ideas remain unproven. One of the strangest puzzles involves information. According to quantum physics, information can never truly be destroyed. Yet when something falls into a black hole, it seems to vanish forever. This information paradox has sparked intense debate for decades. Some scientists suggest that information is somehow encoded in the event horizon itself. Others believe it may eventually leak out as radiation, what Stephen Hawking famously proposed as Hawking radiation. If true, black holes are not eternal. They slowly evaporate over unimaginable timescales, eventually vanishing into nothingness. Black holes also shape galaxies. Their immense gravity powers quasars, the brightest objects in the universe. As matter spirals into a supermassive black hole, it releases energy so intense that it can outshine entire galaxies. These cosmic engines influence the birth of stars, regulate the growth of galaxies, and may even play a role in the grand structure of the universe itself. Despite their reputation as cosmic destroyers, black holes are not vacuum cleaners sucking up everything nearby. A black hole has the same gravitational pull as any object of equal mass. If our sun were replaced by a black hole of the same mass, Earth would continue orbiting as before, though life would not survive without sunlight. Black holes are dangerous only if one ventures too close to their event horizon. Imagine approaching a black hole. Tidal forces would stretch you into a thin stream of matter, a process chillingly named spaghettification. Space itself would warp, and time for you would move differently than for distant observers. Near a black hole, the universe becomes a surreal landscape where the familiar rules of reality twist into something alien. As we learn more, black holes remind us of how much remains unknown. They are not merely destructive voids, they are laboratories of physics, gateways to deeper truths about space, time, and the universe. To study them is to confront the limits of human knowledge, standing at the edge of the cosmic abyss. Black holes are both terrifying and beautiful, embodying the universe at its most extreme and challenging us to question everything we know. Within their mysteries may lie the key to understanding the ultimate nature of reality.
When astronomers first began measuring the motions of stars and galaxies, they stumbled upon a perplexing mystery. Stars at the edges of galaxies were zipping around far faster than anyone expected. According to the visible matter, the stars, gas, and dust, they should have been flung into space. Yet something invisible was holding them together, exerting a gravitational pull without emitting a single photon of light. This unseen substance is what we now call dark matter. Dark matter cannot be seen directly. It doesn't emit, absorb, or reflect light. Yet its presence is undeniable. Across the universe, from individual galaxies to massive clusters, dark matter forms a vast cosmic scaffold. In fact, it makes up about 27% of the universe's total mass energy. Without dark matter, galaxies could not have formed, and the universe as we know it would not exist. Scientists study dark matter through its gravitational effects. By observing how galaxies rotate, how clusters bend light from distant objects, and how cosmic structures evolve over time, they can map where dark matter resides. Despite decades of research, its exact nature remains elusive. Some theories suggest it may consist of exotic particles that interact only weakly with ordinary matter, while others propose entirely new forms of physics. Each experiment brings us closer to understanding, yet the mystery endures. If dark matter holds the universe together, dark energy pushes it apart. In 1998, astronomers studying distant supernovae made a groundbreaking discovery. The expansion of the universe is accelerating. Instead of slowing down under gravity, galaxies are moving away from each other faster over time. This invisible force, driving cosmic acceleration, was dubbed dark energy. It's even more mysterious than dark matter, making up about 68% of the universe. Unlike localized objects like stars or planets, dark energy permeates all of space, acting as a repulsive force that counteracts gravity on cosmic scales. Its effects may be subtle locally, but they dominate over intergalactic distances. If dark energy continues to exert its influence, the universe could expand forever. Stars will eventually burn out, galaxies will drift apart, and the cosmos could become a cold, dark void, a scenario known as the Big Freeze. Together, dark matter and dark energy define the large-scale structure of the universe. Ordinary matter, the stars, planets, and gas we can see, makes up only about 5% of the total. The rest is hidden, yet it dictates the cosmic choreography. Galaxies form along filaments of dark matter, clusters gather where the invisible scaffolding is densest, and vast voids remain where it is absent. The universe is structured not just by what we see, but by what we cannot see. The study of dark matter and dark energy is at the frontier of modern physics. Experiments deep underground, in particle accelerators, and in space aim to detect dark matter particles directly. Observatories monitor the subtle motions of galaxies and light bending through the cosmos, searching for clues about these invisible forces. Yet, despite all our efforts, we are only beginning to grasp the profound implications of these discoveries. Dark matter and dark energy challenge our understanding of reality itself. They reveal that the familiar universe of stars and planets is only a tiny fraction of what exists. Most of the cosmos is hidden from view, governed by forces we cannot see, shaping the destiny of everything. To comprehend them is to confront the limits of human knowledge, to explore the invisible fabric that underpins existence. The universe continues to inspire awe. The dance of galaxies, the bending of light, the vast cosmic web of clusters and voids, all sculpted by unseen forces. Every observation brings us closer to understanding the invisible, yet reminds us how much remains unknown. Dark matter and dark energy are the silent architects of the cosmos. They shape galaxies, govern cosmic expansion, and define the ultimate fate of the universe. Though we cannot see them, they are everywhere, inviting us to explore the hidden depths of reality and confront the profound mysteries that lie at the heart of existence.
The universe is a wild and violent place filled with cosmic catastrophes that can reshape entire galaxies in the blink of an eye. Take supernovae, for instance. When a massive star exhausts its nuclear fuel, it can explode in a brilliant flash, outshining entire galaxies for a brief moment. This explosion doesn't just mark the end of a star's life, it scatters heavy elements across the cosmos, seeding the very material needed for new stars and planets. It's a spectacular cycle of destruction and creation. Then there are gamma ray bursts, the most energetic explosions known to occur in the universe. These bursts can release more energy in a few seconds than our sun will emit over its entire lifetime. Imagine a flash so powerful that it could potentially strip away the atmosphere of a nearby planet. Yet even these cataclysmic events can lead to the birth of new stars, as the shockwaves compress surrounding gas and dust, igniting the process of star formation. Galaxy collisions are another fascinating phenomenon. When two galaxies collide, they don't just smash into each other like two cars. Instead, they interact gravitationally, leading to a complex dance that can trigger waves of star formation. The Milky Way itself is on a collision course with the Andromeda Galaxy, and while it sounds catastrophic, this event is expected to create new stars and possibly even new solar systems. Smaller objects, like asteroids and comets, also play a crucial role in this cosmic drama. The impacts of these objects can be devastating, as seen with the asteroid that contributed to the extinction of the dinosaurs. However, these impacts can also deliver essential materials, like water and organic compounds, to planets, potentially kickstarting life. Earth's own history is marked by such events, shaping our planet's evolution and the development of life as we know it. What's truly fascinating is the paradox of cosmic catastrophes. While they can lead to destruction, they also pave the way for new beginnings. Each explosion, collision, and impact is a reminder of the universe's relentless drive toward change. By studying these events, we gain insights into the fundamental forces that govern the cosmos. We learn about the life cycles of stars, the formation of galaxies, and the delicate balance that allows life to flourish on planets like ours. Understanding these cosmic events is not just about appreciating the beauty of the universe, it's about recognizing our place within it. We are the product of these violent processes, born from the ashes of stars that exploded billions of years ago. Every time we look up at the night sky, we're gazing into a history of cosmic chaos that has shaped our existence. So the next time you ponder the vastness of space, remember that even in destruction, there lies the potential for creation. The universe is a magnificent tapestry woven from both chaos and order, and we are fortunate to be a part of it.
The universe is a vast, ever-changing expanse, constantly expanding since the moment of the Big Bang. Imagine that initial explosion, a singularity bursting forth into existence, creating everything we know. As we look up at the night sky, we're witnessing not just stars and galaxies, but the ongoing evolution of the cosmos itself. One of the most fascinating aspects of this cosmic journey is the accelerating expansion of the universe, driven by a mysterious force we call dark energy. This phenomenon is like a cosmic engine, pushing galaxies apart at an ever-increasing rate. It's a reminder that the universe is not static. It's alive, evolving, and changing in ways we are only beginning to understand. As we contemplate the future of the universe, several scenarios emerge. The Big Freeze is one possibility, where galaxies drift apart, stars burn out, and the universe grows cold and dark. Picture a vast, empty void where once there was light and life. Then there's the Big Crunch, a scenario where the expansion eventually reverses, leading to a collapse back into a singularity. It's a dramatic end, reminiscent of the beginning, but one that raises questions about cycles of creation and destruction. And let's not forget the Big Rip, a more chaotic fate where the universe's expansion tears apart galaxies, stars, and even atoms. It's a wild, almost surreal image of the universe unraveling at the seams. Each of these scenarios paints a different picture of our cosmic destiny, and they all hinge on the nature of dark energy and the fundamental forces at play. But what does this mean for us, for intelligent life? As we ponder our place in this grand tapestry, we must confront the vast timescales involved. The life of a star, the formation of planets, and the evolution of life itself occur over billions of years. Our existence is but a fleeting moment in the cosmic timeline. Yet, it's within this brief flicker that we find meaning, connection, and a desire to understand our universe. Studying the future of the universe isn't just an academic exercise, it's a philosophical journey. It forces us to confront our own mortality and the transient nature of existence. Are we mere observers in a grand cosmic play, or do we have a role to play in the unfolding story of the universe? As we explore these concepts, we realize that we are intricately linked to the cosmos. The atoms in our bodies were forged in the hearts of stars, and our very consciousness is a product of the universe's evolution. This connection is profound, reminding us that we are not separate from the universe, but a part of its ongoing narrative. In the end, the universe is a dynamic tapestry of creation and destruction, a beautiful dance of matter and energy. As we look to the future, we can embrace the uncertainty and wonder of what lies ahead, knowing that we are all part of this incredible journey through time and space.